Hello everyone, here we are with the part 3 of vertical positioning dealing with GNSS altimetry. GNSS altimetry means determination of orthometric heights using GNSS. GNSS altimetry means obtaining orthometric height from GNSS-derived geodetic height. There are 4 methods. One is using a geoidal map. The second one is to create a local geoidal map, merging information from tracking over benchmarks and a geopotential model. The third method is repositioning of a pre-existing geoidal map, and finally creating a local geoidal map using information coming from tracking over benchmarks only. So the first one is obviously the best choice, but there is no clear hierarchy in terms of accuracy. I usually tend to rank them in the order that I'm presenting, but everything depends on the information that we have. Number 5 here is simply disregarding orthometric height, pretending that geodetic heights are the same, they're as good as orthometric heights. We're going to see that this is very dangerous. So let's start with number 1. But first, a note on terminology. In the discussion that we're going to have now, there are 3 terms that are important that we define them beforehand. The first one is geometric geoidal height. We're going to call the geoidal height N, derived from the difference between a GNSS geodetic height obtained on a benchmark with known orthometric height. That is a geometric geoidal height. The other term is gravimetric geoidal height. We will call the geoidal height N obtained from a geoidal map as gravimetric geoidal height. And finally, geopotential geoidal height. We're going to refer to geoidal height N obtained from a geopotential model as geopotential geoidal height. So let's talk about number 1. Number 1 is essentially the direct application of the general expression, the orthometric height equals the difference between the geodetic height and the geoidal height. Or if we think in terms of differential terms, we are talking about the difference between heights between 2 points. So this is basically what we discussed before, using N, the geoidal height, obtained from the GPS-H program from NRCan, and the geodetic height from GNSS. I consider this the most rigorous solution, but we have to keep in mind that geoidal model is just that. It's a model, and it contains uncertainties. The number 2 deals with creating a grid that represents the geoid and constrain it using the values that you derive from GNSS on benchmark. So how do we build this grid? The values of N, of geoidal height, will be built from a geopotential model, which we're going to just explain a little bit more in the next slides. So we will have a grid defined by geocentric latitude and geocentric longitude, phi and lambda. And here we have the equation that is applied, and this equation is a function of coefficients that are a part of a geopotential model. So the geoid that we derive, the grid that we form, is basically have a shape. But the problem is that these values of n derived from geopotential models, they generally are offset from the true geoid. So if we have then benchmarks in the area, we can make GNSS observation on them. We derive geometric geoidal heights, and then we use them to constrain the grid. So that's what we are trying to show in this diagram. The upper diagram, we have the reference ellipsoid, and we have then the geoid in blue that is derived from the geopotential model. Now, what we have also are these green circles. They represent the benchmarks. So, which means that we have point values for these benchmarks. Okay, so NA, NB, and C. So what we have to do essentially is move the geopotential model geoid that we have in blue. Now we move it in such a way that it fits the known geoidal heights that we obtain from the GNSS on benchmarks. Okay, so this is essentially a adjustment with constraints and with injunctions. So anyway, what we have now is we're getting the shape of the geoid. Again, we got the shape of the geoid that we got from the geopotential model. Now we are fitting it with the known information that we have from the local. To illustrate the difference between the geoidal height derived from geopotential model and the geoidal height derived from GNSS over benchmarks, I'm presenting this table, which contains the difference between these two quantities over Mexico and over Canada. So what we have here is a comparison based on different geopotential models. So each one of these is a different geopotential model. And here we have the mean values. Okay, for Mexico, we can see that it is all around 5, 6, 7 centimeters with maximum and minimum values at the range of 1.9 and the highest would be 2.3. Okay, so for Canada, it's the fit is slightly better, and well, I'll say it's much better. It is at the range of 2 centimeters maximum, and well, roughly 3 centimeters maximum in mean terms, but in terms of minimum and maximum, we have also values that vary between plus or minus 1.3 to 1.5 minus 1.5 meters. So which means that it is important. Again, the geopotential will give the shape, and then we constrain this shape of the geoid with the GNSS on benchmarks. Just a little bit of explanation about geopotential models. The geopotential models are basically a collection of the geopotential coefficients. Okay, these geopotential coefficients here we have with these C bar means that they are normalized. They are obtained from satellite missions. Okay, and of course there are a series of different geopotential models. They started to be built since the 1960s with the space age. So in this expression, we have the geoidal height in here for a particular point of spherical latitude and spherical longitude. So Gm is the Earth gravitational constant. R is the geocentric distance to the computation point on the ellipsoid. So this is radial, so that's a spherical approximation. Gamma is the normal gravity. R is the radius of a reference sphere, which is usually taken as the value of the major semi-axis of the reference ellipsoid. And N and M are degree and order of the spherical harmonic expression. So this expression here is what we call a spherical harmonic expansion, actually. So this PM bar and M is the normalized associated Legendre functions. And how can we evaluate this value of N? Well, as a matter of fact, we can use some pre-existing tools. For example, in this link provided here, we can build a grid of geoidal height values using the EGM 96 or the EGM 2008. The EGM means Earth Gravity Model, and it's the model associated with the WGS 84 ellipsoid. We can also go to the website of the International Gravity Field Service and use the tools that they provide. In this website also, there is a list of several geopotential models. So it is perfectly doable, this approach. The third approach is a variation of the second. Okay, if we think that instead of having the shape of a geoid coming from a geopotential model, what we have is an old gravimetric geoid. Let's suppose that there was a geoid in a particular region that you're going to work with, and this geoid you may not trace back its origin, or you may know that it was determined using well, old methods or whatever. So what you can do is you can get the shape of that old gravimetric geoid and constrain against GNSS on benchmarks. Again, we need to have benchmarks in the region. What happens if we are working with in a region that there are no no information whatsoever, but there are very good. Let's suppose that you have good benchmarks. Okay, so something that was really widely used was just to build a geoidal map, a local geoidal map, using the geoidal height derived from GNSS on benchmarks only. So if we have enough benchmarks, we're going to have enough values of n, and then we can approximate with the surface. Okay, and then we interpolate the values of n for the desired points. As an example that I use, and this has some sentimental reasons for me, this is an old project back in the 90s that I did. It was exactly for building a local geoidal map. So we have these benchmarks that were located around two highways, and this is a geodetic marker which had orthometric heights, and we were interested in getting the geoidal height for this point in here. So we did, of course, GNSS on benchmarks, and the values of n were interpolated, and voila, this is the local geoidal map. Now, number 5, that's something that I don't recommend anyone to do, but I have seen people doing it, okay, and committing big mistakes. is to consider the geodetic height, the height derived from GNSS, as the same as the orthometric height. What's the problem with that? So this figure tries to show what is the big risk on that. So let's suppose that we have a flat surface. We can think that we have, say, a lake here, okay? And therefore, the height, the orthometric height of point B and point A are the same. Okay, I drew the geoid flat as well, just to make sure that we can clearly see that the orthometric heights are the same. But the ellipsoid, we know the ellipsoid is not parallel to the geoid. Okay, therefore, the geodetic heights of point A and B, with all likelihood, will be different. And with a even increasing likelihood, they will be very different. Okay, so not just the numerical value of the geodetic height, the geodetic heights are different from the orthometric heights, but the numerical values of the geodetic height of A will, with all likelihood, be different from the geodetic height of point B. And that's what I am emphasizing here. Okay, so this is really not a approach that is recommended.